Welcome back to Algorithmic Game Theory. In the last lectures, we introduced mechanism design with money. We got to know the notion of a truthful mechanism, and then also, via Meyerson's lemma, we got a pretty great characterization of what it is that makes a mechanism truthful for single parameter settings. Today, we'll use this characterization to build truthful mechanisms for combinatorial auctions. This means that we'll have to design an outcome rule, which is nothing but an algorithm that decides how to allocate items. And then, from Meyerson's lemma, we'll conclude what payment rule we would have to apply so that we get a truthful mechanism in total. This won't work for general combinatorial auctions, but only for a subclass which we can again understand as a single parameter setting. Because for arbitrary settings, which are not single parameter, Meyerson's lemma does not hold. And by the way, things are much more complicated. Good. So let's first recap the definitions of combinatorial auctions. In a combinatorial auction, we have n bidders or players, however you want to call them, and that will be a set capital N, and usually we call it the bidders 1 through n. And then we have m items, and we call that set M. Usually we might also call the items 1 through m, although we might not always do this depending on what feels right at that time. What are now feasible allocations? Feasible allocations are vectors of sets. So each of these sets is an element of the power set of the set of items. And we also want that each item is allocated at most once, which means that if we consider what bidders I and I prime get, those two sets have to be disjoint unless I is equal to I prime. We'll have valuation functions. Those define a non-negative value for every set of the items for each player. And those are private information. And what will our objective be? Our objective for today will be to maximize social welfare. So we might add up the values that the players have for their respective sets of items that they're getting. We'll assume furthermore free disposal, which is a very fancy way of saying that if I get a set of items S, my value is at least the value I would have for the set T if T is a subset of S. In other words, more items never hurt me. If I get more items, so if T is a subset of S, then the value I have for the set S will be at least as much as my value for the set T. You could also call this simply monotonicity. And then we also assume that valuations are normalized. Which means that the value of the empty set should be 0. So if I don't get anything, my value is 0. If I get more, then my value will be non-negative, because we're saying that the value for such a set will always be non-negative. Good. Now, this is generally not a single parameter setting. Why that? Because these functions, they cannot be expressed by just a single parameter, which is exactly the point of a single parameter setting. But the special cases of valuation functions we're considering today, those we can indeed interpret as a single parameter setting. Namely, what will our assumption be? Our assumption will be that I'm single-minded. I'm only interested in one subset of the items. If I get at least this subset, then I'm happy. If I don't get it, then I'm just as happy as when I don't get any items. Let's write this down formally. We say that bidders are single-minded if for every bidder there exists some set SI star of items and some non-negative real VI such that bidder I's value for a set of items will be VI if T is a superset of SI star and 0 otherwise. So, we are again overloading notation here. By VI, we both denote the function as well as the value that it can take. And this, I think, should be very familiar by now, because in the case of, for example, a single item auction, we did exactly the same. Or also in the case of the single parameter settings. So VI, that is my value for the set SI star. If I get at least the set SI star, meaning I might also get more items, then my value is always VI. But if I don't get all of SI star, and this might even mean that SI star contains 100 items, I'm getting only 99 of them, always then my value will be 0. Good. Let's see how we can visually understand this. In my example here, I now have two items. Let's call them A and B. And then I have three bidders. The red bidder has a value of 10 for item A. For getting item B, this bidder does not have any value. For getting items A and B together, this bidder still has a value of 10. Because you don't care what you get unless you get all the items that you want. So all that matters is which are you getting all the items that you want. The blue bidder may look something like this. So they have a value of 8 for item B, and also a value of 8 for A and B together, and a value of 0 for only item A. And of course a value of 0 for getting no item. Now we'll also have this green bidder, and they now could have, for example, a value of 14 for both items together. And this now means that if this bidder is getting, for example, only item A, the value will be 0. If this bidder is getting only item B, then the value will be 0. The value will only be 14 if they're getting both items A and B. Good. What's the optimal social welfare here? The optimal allocation would be to give item A to the red bidder, item B to the blue bidder. This would give us social welfare of 18. Good. Now our goal is to design a mechanism for this setting. As you remember, these valuations, they are private. Well, we will now make our life easy, although this is strictly not necessary. We will assume that we already know these sets Si star, that those are actually public knowledge. And the only thing that is private knowledge is this Vi. So I don't know your value for this set of items. So for example, in advance we already know that bidder A has the red bidder has a value of has a value for item A, but we don't know what value it is. And what's our goal now? So our goal will be to design a mechanism M consisting of an allocation rule and a payment rule. By the way, to just avoid any confusion, I'm now writing this M for the mechanism as such a calligraphic M, whereas the set of items, which we also call M, this will be a printed M. Now F will be an outcome rule, P will be a payment rule, and they both take as input some bids Bi, and we now assume that this vector of sets that the bidders want, this is actually public knowledge. And what are our design goals? I hope you remember those. Our goals should be that we'll have a truthful mechanism. So M should be dominant strategy incentive compatible. At equilibrium, meaning if everybody tells their true value, the mechanism should obtain high social welfare. And also, the mechanism should run in polynomial time. Or more precisely, we want this mechanism to run as fast as possible, and something that we've kind of agreed on in computer science is that polynomial time is fast, not polynomial time is slow. You could still ask other questions like if you wanted to allow exponential time, but we are restricting ourselves to polynomial time algorithms here, and this will actually be our first insight now, that within polynomial time we cannot actually obtain optimal social welfare regardless of whether we are dominant strategy incentive compatible or not. So all this truthfulness, that's actually not our first hurdle that we see, but rather that solving these combinatorial auctions exactly, that this is an NP-hard optimization problem. The first thing that we should now talk about is, can we expect to exactly solve this combinatorial auction problem in polynomial time, or why not? Because it is NP-hard. This is our first claim that we want to show. More precisely, even the allocation problem among single-minded bidders is NP-hard. I guess in your life you've seen enough NP-hardness proofs so that we won't have to go through this in all details, but let me only give you the idea of why this is a hard problem, because this is really easy to see. Namely, if we were able to solve this problem exactly, this allocation problem, allocating items among single-minded bidders optimally so as to maximize social welfare, then we could also solve independent set. How so? So we will show a reduction from independent set. And how do we now transform the input? If we are given a graph, what we'll do now is very simple, namely, we'll set the set of bidders to all vertices and the set of items to all edges. And for a bidder now, set the set Si star to be the following. We'll let it be the set of all edges whose endpoints, such that I is one of the endpoints. So this means in our graph, we represent our graph as follows. So what will this look like? Well, just suppose we might have this kind of a graph. Then we'll interpret this by 4 items, 1 for each edge, and 4 bidders. Namely, for example, we might have this bidder who wants to get the first 3 items. Then we'll have, for example, this bidder who only wants to get the first item. We'll have this bidder who wants the second and the last item. And we'll have this bidder who wants to have these 2 items. And something that I forgot to mention earlier, we want to set the value for winning the items, for winning all of the items, to 1. Now what you can see here is that if you find an allocation which maximizes social welfare, what you maximize is just the number of bidders that you make happy, who you give at least their sets of items. But for each edge now, it will not happen that both endpoints will be selected because, and that's exactly the point of one of the items being the point of the edges being represented by the items, that, for example, if we're now considering this edge here, this corresponds to this item, and then now this means that either this purple or the blue can be the can get this item, so we cannot give the item to both of them, and which means that in our independent set also only one of the 2 can be contained. Good. So please go ahead and figure out the exact details yourselves, but I hope that, given that you're probably pretty familiar with NP hardness proofs, this is nothing too extraordinary for you. So what we'll focus on instead today is what can we still do? Namely, what we of course want to do is we want to approximate the optimal social welfare, and we want to find an algorithm which gives us a provable approximation, and then at the same time there are still all these incentive issues which we haven't even talked about yet. So more precisely, what our goal will be to find an alpha approximation to social welfare, to the optimal social welfare, I might want to say, which means that the sum of the VI of SI should be at least 1 over alpha times the maximum of all S prime, sum of all VI of SI prime. And fortunately, as we will see today, for single-minded bidders, getting such an approximation algorithm, which gives us a good factor of alpha here, is not too difficult, because simply greedy algorithms do the trick. And not only this, we can also combine them via our insights in Meyerson's lemma with a payment rule, such that we obtain a truthful mechanism. The first thing I'd like to do now is see a very simple greedy algorithm for single-minded combinatorial auctions. And then we'll also see that this algorithm is monotone, and this is why we then get truthful payments, or payments that make this a truthful mechanism, to be more precise. And then we can also just derive very explicitly what the payments will look like. Before that, let's introduce one more piece of notation, namely, we now say that if bidder I gets a superset of the desired bundle Si star, then we call I a winner. So our goal is nothing but to determine a winner set W where we still have the property that if I and I prime are in W and they are distinct, then their desired sets have to be disjoint. Good. Now, how can we do this? We can do this in a very simple way, namely, we can consider the following greedy by value algorithm. We'll be reordering the bids such that we now say the first bidder has the highest bid, the second bidder has the second highest bid, and so on. And now we'll initialize the set of winners as the empty set, and we now consider the bidders by now increasing index after ordering, and we say that if the bundle of this bidder we're currently considering is disjoint with all bundles that we've seen so far and accepted, then this bidder will become a winner as well. Okay, so what does this mean? This actually means something very simple. Let's consider our example from before. We initialize the bids, the winner set as empty. We order the bids by decreasing size, or by decreasing value. So we'll first consider the green bidder, who was bidding 14. Then we're considering the red bidder, and only then we're considering the blue bidder. We'll now see, okay, this bidder was bidding 14. This is the first bidder we're considering. And we see the set of winners was empty so far. So this here is fulfilled. which means we'll accept the green bidder first, and then we'll consider the red bidder, and we'll see, okay, at least one of the items has already been allocated, so we are not making this red bidder a winner. Same will be true for the blue bidder. So what we're observing here is that we are not ending up with the optimal social welfare, because this would be 18, but we are getting only 14. Nonetheless, we'll be able to prove a reasonably good approximation factor. But before we do that, let's first talk about truthfulness. Why can we turn this mechanism into a truthful mechanism? And as you realized, I didn't actually distinguish between whether these are the true bits or whether these are the true values or only some arbitrary bits. The point being that later we actually will just rely on every bidder bidding that true value. And then this means that if we get good welfare with respect to the declared bids, then assuming that these bids represent the true values, then we actually obtain good social welfare. But as I was saying, let's first talk about truthfulness. And the first thing I'd like to define is the following. Let W of B be the set of winners when bids are B. And now we'll define tau I of B minus I as the following. Take the infimum of all bi such that I is in W of bi, B minus I. And this is what we call the threshold bid or the critical bid for bidder I against B minus I. So what does this mean? Suppose you are player I, and you now fix the other bidders to bid B minus I. How much would you want to bid if you want to become a winner? Well, among everything that you can bid, tau I of B minus I, this is the smallest bid that will make you a winner. Because this might not exist, we're actually writing the infimum here rather than the minimum, but just think of this as being the minimum. So this is the smallest bid that makes you a winner. This is actually a crucial thing if you, for example, think of a first price auction, because there you definitely want to bid this threshold bid or the critical bid, because this is the bid that lets you pay least and still win the item. Here, of course, we won't be using these first price kind of payments, because those won't yield a truthful mechanism, but still it is very related, because eventually this will just be our payments. How does this turn out now exactly? Greedy by value is a monotone algorithm and charging winners the respective critical bits yields a truthful mechanism. Okay. So how do we prove this? The first thing I'd like to talk about is monotonicity. And something we haven't yet talked about is how is this actually a single parameter problem? How would we capture this in the notation of Meyerson's lemma? And how we could also write this as follows. In the single parameter notation, we could now set fi of b to be 1 if I is a winner and 0 if I is not a winner. To prove monotonicity, what will we have to show? We'll have to simply observe that if I am a winner now, then I will also be a winner if I bid more. How so? Well, to see this, we'll have to go back to our algorithm and see what would now change if you increased your bid. Well, suppose you are somewhere here and now you increase your bid. What will happen? You will kind of move further to the front. And what does this mean for this condition here? The set of winners that have already been selected when this while loop is coming to ask you, this will only be smaller than, which means it is just easier that all of your items are still available. By the way, there is a star missing in here. Those are just always the bundles that these items, that these bidders just want by their single parameter property. Good. So the point is, if you're a winner and increase your bid, then you'll only move further to the front. This is why this is a monotone algorithm. Good. Now, what does this tell us regarding payments? By Meyerson's lemma, M will be truthful if we set PIB to the following bi times fi of b minus the integral from 0 to bi fi of t comma b minus I dt. Or just because this always helps to understand this pictorially, the allocation function will look something like this. Now, how big will the payments have to be? How big is this? This is exactly the area above the curve. So for example, if you're bidding this much here, where this is bi and this is fi of b minus I, here we'll have 1. If you're bidding this much, then how much will you have to pay? You'll have to pay exactly this area here. And how is this point here called? This is exactly tau I of b minus I. Good. If you prefer, you can also now just do this from the integral equation. You will get to the exact same point, namely that the payment will be bi times fi of b minus this integral. How much will this be? This integral here, this will be exactly the integral from tau I comma b minus I up to bi of just 1. And this means all this together will be tau I of b minus I. And this is of course only true if we have a winner. You are a winner if your bid is right of this tau I of b minus I. And if you're a loser, then this is 0, this is also 0, then you're not paying anything. So pi of b will be 0 if you are not winning. And this already proves the first claim, namely that, well, as we've convinced ourselves, this is a monotone algorithm, and we get a truthful mechanism if always the winners pay the respective thresholds bids and the losers don't pay anything. Good. Now what we'll still have to talk about is what kind of an approximation guarantee are we getting? And what we're claiming is the following, that greedy by value is a D approximation where D denotes the maximum cardinality of these desired sets Si star. Good. How do we show such a thing? Well, we show this actually like we show all approximation guarantees, namely we see what does our algorithm do versus what does the optimal allocation, the social welfare maximizing allocation, do. In more detail, we let W be the set of bidders who are selected winners by the algorithm and we let opt be the set of winners chosen by the optimal solution. What is our claim? Our claim is that the sum of all I in W bi, this will be at least a 1 over d fraction of the sum of all I in opt bi. At this point, I'm actually not quite sure whether I want to write vi or bi. You can do this whatever you like, because you could now say, okay, I'm just analyzing what happens when I'm doing this with the true bits, because we can just hope, because we have a truthful mechanism, that we're actually seeing the true valuations. Or you can say, okay, I'm just doing this on any sort of bids, and now I'm just saying, okay, on these bids, I want to give a good approximation. This doesn't actually make any difference. The point eventually will be, combined with truthfulness, we will actually, in the equilibrium, maximize social welfare approximately within a d factor. How do we show such a thing? We do now a simple charging argument. Namely, we now say that every bidder who is an opt could, in principle, get the items unless some other bidders have taken items away before. And more precisely, we'll do this as follows. For is set for a winner of our algorithm, we let now opt I be the set of all winners that would be chosen by opt that have a larger index and that collide with SI in a way. So, at some time we are choosing I as the winner, as a winner, and this way we are pushing other winners that opt would be choosing out of the solution. Namely, we are the following bidders we cannot select anymore after having chosen I. The following from opt we cannot select anymore. Those are exactly the ones who want also one of the items that we have just allocated. By the way, what does it mean if I itself is an opt? Then this set contains exactly the ones in opt who have a non-disjoint intersection with SI star. But if I is itself an opt, then this set will also contain simply I. But in other settings, and this is the way you should think about this, these are exactly the ones that we're losing from opt because we are accepting bidder I. And what we now observe is that each j in opt is contained in at least one set opt I where I is a winner by our algorithm, chosen by our algorithm. Why is this true? Because if j is not an opt I for all j which are for all I which are smaller than j, then the algorithm can accept j when reaching it, and will do so, of course. And then j itself will be a winner, and opt j will be exactly the set containing only j. With this insight, we can now rewrite this bj of the j in opt as follows. We can now say, okay, this will be at most, take the sum over I, all I in w, take the sum over all j in opt I, bj. Why that? Because everything that we have here on the left-hand side, this is just taking the sum over all j in opt. We now know that all these will also show up in at least one set opt I for an I in W. Good. And now, what we can do is, we can now see how big will these sets opt I be. How many j in opt can some bidder I exclude from the by being selected? Well, we know that each of them will have a non-empty intersection with Si star. And those all use different items. Their items are disjoint. So this means that here opt I, the cardinality of opt I, will be bounded by the cardinality of Si star. And this immediately means that it is bounded by D. And what does this tell us? This tells us that this sum we have here, sum of all j in opt bj, this will be, yes, we know, at most this double sum. but this will also be at most d times bj bi. Why is this? Here we're using one further thing, namely that bi is at least bj for j in opt I, because we used this reordering. We reordered the bidders accordingly. So we're getting d times the sum of all I in w bi. And interestingly enough, I guess, this is exactly what we wanted to show. This is equivalent to this guarantee. Good. So what happened here? We used that every bidder can only block d bidders from the optimum, and also the bidders that it is blocking, those have a smaller bid than our own bid. And this is why we get this chain of inequalities. Good. Now, this is nice for the setting where each bidder wants only a small number of items. So take, say, like 2 or 3 or 4, and then this will be a 2 or a 3 or a 4 approximation. But could we analyze this algorithm in a smarter way? Because this might get very large if d becomes large. Unfortunately not. Namely, what could happen here is the following. We could have d items and we'll have now many blue bidders who each have a value of 1 for one of the items, but at the same time we'll have a red bidder who would have a value of 1 plus epsilon for all items. What would happen here? Who would get the items? Well, it would be the red bidder, because the red bidder has a value of 1 plus epsilon for all the items, whereas the blue bidders only have a value of 1, and we don't care how many items they want. If we now have multiple copies of this, we'll also have m items in total. Here, those are only d items. But because we are totally neglecting the fact that one bidder might want many more items, so d more items than another bidder, we are actually not getting any better guarantee than a factor of d. You might now be tempted to say, okay, now I divide by the size of the bundle that they want. Then the exact same thing can happen, but the other way around. And this is for a good reason. It is because there's also a hardness of approximation result, which shows that more or less you cannot be better than a d approximation in this setting here in polynomial time, of course, under certain complexity theoretic assumptions. But what you can do better is if you have really many items, and if your d also gets large, then you actually can get a better guarantee, which is then stated in terms of m, the overall number of items. And this we will be considering next. So after having now seen the greedy by value algorithm, we are considering next an algorithm which works better if you have large bundle sizes, which means if this d, which was the maximum size of a desired bundle, was large. And how does this algorithm work? it normalizes the bits in a way that it divides them by not the bundle sizes, but by the square root of the bundle sizes. And mysteriously, this is somehow a sweet spot that gives a better approximation than if you did not divide the bits by anything or dividing the bits by the bundle sizes, which, as I was claiming earlier, won't give you a better guarantee. What does this algorithm look like? So I call this greedy by square root value density. And what we do is we reorder the bits again. Before we were reordering the bits such that they are in a non-increasing sequence. Now we first divide every of the bits by the size of by the square root of the size of the respective bundle that this bidder wants. Then we again initialize the winning bits to the empty set, and we also run the same for loop that we've had before, namely if none of your items has been taken away so far, then we'll add you to the set of winners when it's your turn. And for this, we can actually show a better approximation guarantee. Namely, we can show a better approximation guarantee if these sets, or if the biggest of these sets SI star is very large. Namely, we can show the following. Greedy by square root value density is a square root of M approximation. Moreover, it is monotone, so charging threshold bits makes it a truthful mechanism. Good. Now, this second part of this theorem, I hope, isn't too surprising at all, because we are more or less using the same kind of an algorithm that we were using before, and we were assuming that this SI star, those are public knowledge. So you cannot even influence what you are divided by, what your bit is divided by. And then the same thing happens. If you're, for example, third in this order, and then if you bid more, then you only move forward. Good. So this second part, this works exactly the same way as we saw this in the case of greedy by value. All I want to talk now is why we get this improved approximation guarantee. And what we'll again define is this opt-I. This is again the set of all j in opt, which come after I in the order by bid, now then by normalized bid, and which we are excluding by including bidder I into our solution. And what's our claim now? Our claim is again that sum of I in W bi, this will be at least 1 over square root m fraction of the I in opt bi. Again, we can rewrite this set of the j in opt bj. I'm now calling them j to now be able to do this step. We could instead take the sum over all I in W and then take the set as sum over all j in opt I bj. This is exactly the same step that we've done before. So all that remains to show is the following, that the sum of all j in opt I bj is at most square root m times bi. Why is this any helpful? Because if we can now show that this here is at most square root m times bi, then you see we get exactly to something that is equivalent to what we want to show. So before we were saying, okay, now this set opt-I, this might be small, and these bj, those can only be smaller than bi, and we were done. Now things are a little more complicated, and what we will replace this by is exactly this bound here. Good. Let's see why this is true. What do we know if j is in opt-I? This means that j is at least I, so bj divided by the square root of the size of sj, this will be no larger than bi divided by the square root of the size of si star. What does this give me? This gives me that the sum of all j in opt-I bj, this will be at most bi over size of Si star times the sum of all j in opt I square root of the size of Sj star. Now we'll use Jensen's inequality. What does that state? It says that for any y1 through yl, which are non-negative, the average of the square root of the y's is at most the square root of the average of the y's because the square root is a concave function. So more generally, you would actually state this, instead of writing the square root here, you would just say for any concave function you have this. Good, but now, because we have a concave function, this is what we can observe regarding the square root. And now let's multiply this by L. So then we're getting that the sum of these square roots of the y's will be at most square root of L times the sum of these y's. In particular, we can now apply this to this interesting sum here, because this is exactly a sum of square roots of non-negative numbers. So what we're getting from this is that this sum of all j in opt I square root of the size of Sj star, this will be at most, how many terms are we adding up? This is exactly cardinality of opt I, and then we'll be taking the sum over all j in opt I size of Si star as j star. Good. Moreover, the size of Si of opt I will be at most Si star. Why that? Because, and this is actually an inequality that we used before, but let me once again make the argument. In opt I, we have all the bidders that we're losing because we are accepting bidder I. Now to count these, the ones from the optimum that we're losing, to count these, we might as well count the items in Si star, because for each item in Si star, we're losing at most one of the bidders from opt I, because they have disjoint sets as J star. Good. So this already helps us here. And what else do we know? We also have that the sum of these j in opt I, cardinality of j Sj star, this cannot be more than m. And this is exactly the same kind of an argument, because this sets Sj star for j being an opt those have to be disjoint. So we're summing up their cardinalities, and this will be at most the number of all items together. Good, if we combine this, then what we're seeing here is that this sum we're trying to bound here, this is at most the square root of the size of Si star times m. Now, where were we coming from? We were coming from here. We now have a bound for this. And now we can just combine this. Where are we getting? We are getting to the sum of all j in opt I, bj, that this is at most bi over square root of Si star, and then we multiply this by this thing here, size of Si star times m, and this is square root m times bi. Good. And this is exactly where we wanted to get. So we are done. Good. So overall, we get a better approximation guarantee if this D, the maximum number of items that one bidder wants to have, is very large. The rest just remains the same, so we still have a greedy algorithm, and this greedy algorithm can be turned into a truthful mechanism via these threshold payments. Of course, here you can again ask the question, could we analyze this algorithm in a better way? Is there a better algorithm? And the answer for both is no. Why that? Because the following thing can happen. You will now have m items, and again you have blue bidders who always have a value of 1 for each of the items. So each one of them has a value of 1 for their respective item, and then there's this other bidder who has a value of square root m plus epsilon for all items together. What will the greedy by square root density algorithm do? It will see, okay, if I now divide by square root size of the set, then this red bidder will seem to give me more value. So I'm taking this red bidder and not the blue ones, and this is exactly where we're losing this factor of square root m. But not worse than this. And you can also not find a better algorithm. So even any smarter algorithm than that you might want to design will not give you approximation guarantees which will be a lot better than square root m, because again there is a hardness of approximation result. This is actually inherited by hardness of approximation of independent set. We saw this this reduction from independent set, and this also translates more or less a hardness of approximation result. And so also for this setting, you cannot hope to get a much better approximation. And the interesting thing is, it doesn't even matter whether you want truthfulness or not. All this truthfulness we didn't even talk about in this second part. It's only because we are insisting on polynomial running time. So as you see, there are settings in which truthfulness more or less comes for free. You just design an algorithm and you want to design the algorithm at least keeping monotonicity in mind, but that's about what you need to take into consideration. These greedy algorithms, those feel so natural that you might have just designed them without ever having heard of monotonicity, of threshold bits, of truthfulness. For other problems, things are not quite as simple. There you actually have to put a bit more work into to get a truthful mechanism, to get a monotone algorithm, because not every algorithm is monotone. I wanted to show you an example here of a non-monotone algorithm, but then it turns out that they are usually so complex that eventually, to first of all understand the algorithm and then to understand the example, this is usually not too easy to see, but trust me, at this point there are these examples of seemingly very natural algorithms which turn out not to be monotone. Good. So all of this is for single parameter settings of some sort. What we'll be talking about next time is what happens if we are beyond a single parameter setting. Because then suddenly all this nice characterization of Meyerson's lemma doesn't work anymore. And indeed, things become a lot more complicated, although if you don't insist on polynomial running time, then you get still a very nice and clean mechanism, which we'll get to know next time, to even exactly maximize social welfare, and which is still truthful. However, as you see, at least for combinatorial auctions, the allocation problem is usually, unless you're considering other special cases, is usually NP-hard, and it's not even easy to approximate it in a good way. So there is still work to do, and this is still an open research area to design truthful mechanisms for combinatorial auctions, although this won't be for single-minded combinatorial auctions. There, Meyerson's lemma actually gives us everything, but for the case that now bidders want, okay, give me this or give me this. For this first thing, I have a value of and for the second thing, I have a value of That gets much more complicated. But as you will see next time, there are also very nice results on this. So, hope you enjoyed this today. Please let me know if you have any questions, and stay safe. Bye.